start talking about matrices next. Have you guys ever seen matrices at all to this point?
I've seen the movie Matrix.
You've seen the movie? So, no, not really math related, but. So, this is going to be a new concept. We're going to do, this is really going to take us to finals. We're going to do this topic, and then we'll talk about a few basic matrix operations, which will be really simple for you guys, and then that will be what carries us through the finals. So, first of all today I wanted to talk about what a matrix actually is and how to write a matrice, and then that's the main part that we need to get through. You don't necessarily have to write all this down. As we see more and more of them, you'll know what it means, but so this is just kind of for us to talk about. A matrix, or matrice if you have more than one, is a rectangular array of numbers enclosed in brackets. Okay, each number is called an element in our matrix, so you don't necessarily have to write these down. What it looks like is something like this. So this whole thing is called a matrix. Each of these numbers would be an element within that matrix. We refer to these as rows and columns. Rows are horizontal, columns are vertical. So this matrix has how many rows? 2 rows and how many columns? 3 columns. Okay, so that would be our matrix. We'll talk a lot about the size of matrices when we get ready to do operations with them. So when we're talking about the size, and we'll go over this again, we'll always count the number of rows and columns. What matrices are used for is to take these systems of equations that we've been doing and pull out the coefficients. It's going to drop off all the variables and write something with just coefficients. Now, the reason behind that, if you go into a field and you're dealing with a lot of numbers at a time, like if you're going into computer programming or something like that, you have lots and lots of numbers to deal with. And so this is a way to kind of pull out the important information and condense it into one place. For our purposes, we are just going to deal with small matrices because I don't want to confuse you with huge ones, but this is probably the most important part to today. We've been dealing with systems of equations that look like this. We are going to take these systems and turn them into what's called an augmented matrix. In this, your variables need to be alphabetical order, x, y, z. And then you do equals and your constant. And so when you write your matrix, you just put the coefficient for x, the coefficient for y, the coefficient for z. This vertical bar represents our equal sign, and then your constant. So all you have to do is line them up. So you notice everything here in my first column, those are the coefficients of my x's in these equations. Second column is your y coefficients. Third column is your z. Last is what it's equal to. If I didn't have a z in one of the equations, what do you think I would put in there? A 0. You have to have placeholders. You can't just leave out a number. So if you are missing one, you'll just put a 0 in its place. When we talk about the size of a matrix, we will say rows by columns. So, for instance, the size of this matrix, how many rows do we have? 3. How many columns do we have? 4. So this is a 3 by 4 matrix. 3 rows, 4 columns. So this section we are going to be solving the system. So we just got done taking a quiz over solving systems of equations using substitution and elimination. We are going to learn how to solve them when it's written like a matrix instead. Now, if you look at the amount of work when we had just 2 equations, it was really easy to do substitution or elimination. When I added in that third equation, it made a lot more work. Think about if you had 5 or 6 equations, substitution and elimination become extremely time consuming. The matrices would save you time in that scenario. Now for the small ones, if it's only 2 systems, the matrices would be more time consuming than substitution or elimination. There's a trade-off. But just for a couple equations, what we've been doing is more efficient, but when you get to more equations, this is more efficient. In the next section, we will also talk about like adding and subtracting with matrices as well, and that does show up on the ACT sometimes too. Okay. So, first thing I'm going to do, I'm going to skip this slide because I've already talked about that. We are going to write the augmented matrix for each of our systems. No. If they both have 2, then you're okay. So the first one we just go alphabetical order. My x is 3, my y is -4. How do I represent the equal sign? Vertical line, and my constant, is -6. Second one would be a 2, a -3, and -5. What is the size of this matrix? 2 by 2 rows, 3 columns. Second one we have to be a little more careful on. The first equation is fine. My x is 2, y -1, z is 1, equals 0. What's wrong with the second one? Out of order. You always need the constant to be on the right side of the equal sign, so the first thing I would have to do is add that 1 over. So then my x is 1. Do we have a y? 0. Z would be 1 and it equals 1. What's the last one going to be? Okay, because you would have to move the 8 over. There is no z, so it would look like this. What's the size of this matrix? 3 by 4. Alright. You guys do C. Write the matrix and the size for me. For the first one.
2, 3.
And the second one? -2. Size of this? 2 by 3. You have to move the constants over on both of those. Alright. Any issues with this stuff? Okay, let's go the other way. So I'm going to give you a matrix. We're going to write the system of equations to go with it. So the first column represents your x's, second is your y's, this is equals your numbers. So the first equation would be?
5x
second equation? You don't have to use x's and y's. You could use a and b, whatever you wanted here. I just typically go x, y, z's. But why don't you guys do b on your own? So first one would be on the second equation, my y has a 0 in it, so you just leave it off. So it'd be 2x plus 2z equals 8. And the last one would be, okay. Are we okay with this? All right. We've got about 7 minutes left. The last thing I want to do, I'm going to have you guys write down something, and this is going to be the stuff that we pick up with on Tuesday. Okay? So you do need this in your notes. We are going to make a list of our legal matrix transformations, the things we can do with a matrix. Okay. The rows of our matrix just represent the equations. When you have a system of equations, does it matter which one is first and which one is second when I give you the problem? No. So we can switch any two rows. We can put whichever one we want on the top. That is a legal move. Okay, second thing we can do. When we had a system of equations, and I told you to solve it by elimination, you would always take one of the equations and multiply it by something, right? So that is a legal move. We can multiply or divide a row by any number except 0. Because if you multiply by 0, you just cancel the whole thing out. Make all the problems easier.
Yeah.
Okay. The last thing we did is, in elimination, we would multiply by something and then we would add our two equations together. So it is legal to add our rows. And not just add rows, you could multiply them first and then add. So I am going to say it is legal to add or subtract multiples of rows. So maybe I want to take this row times the 2 and then add them together. That would be a legal option. Okay, we are going to do 2 very basic examples, just talking about a row operation, and then we're done. We are going to be using a notation next week for talking about our operations. And it's going to look something like this. We will have subscripts to tell us which row we're talking about. When I say capital R2 equals, that means we are going to change row 2. So I am changing this one down here. And then we will describe how we are going to change it. So, in this, I'll give you a second to write it down. We are making a new matrix by doing this operation. This operation is only changing row 2, so row 1 is going to stay the same. Okay, to get my new row 2, we're doing -3 times row 1 plus row 2. We do that for each entry. So, what that means is for this first number right here, I do -3 times the number in row 1 right there, which is a 1, plus the number in row 2, which is a 3. So -3 plus 3 would make this a 0. And we're just going to repeat that operation for each one. So for this entry, we're now talking about the second column. -3 times row 1. The number in row 1 is -2, plus the number in row 2, so that gives me 6 plus -5, which is 1. Last one. -3 times the number in row 1, which is a 2, plus the number in row 2, which is a 9. So -6 plus 9 is 3. And that's my new matrix. Questions about